So when we talk about our rectangular coordinate system, our points are of the form x comma y, and x is the horizontal distance that you move, and y is the vertical distance that you move. When it comes to the polar coordinate system, our point is written in r comma theta notation, and r is a directed distance from the pole, and theta is a directed angle counterclockwise from the polar axis. So in our rectangular coordinate system, we have an x-axis and a y-axis and an origin, right? Kind of think about that origin as being your pole, okay? The very center of this coordinate system, and then your directed distance, or your polar axis, is going to be what would normally be the positive x-axis in a rectangular coordinate system. So we'll talk about angles in relationship to that. Where are they? Counterclockwise movement. And we'll talk about how far we are away from that pole. So far, so good? All right, so next, we're going to plot and label some points. And I'm going to ask you to do this a little bit out of order. We're going to start with A. So I want you to plot 2 comma pi over 6. So we're looking for a point that's 2 out with a directed angle of pi over 6 counterclockwise from our pole. So pi over 6 is how many degrees? 30, right? Anytime it has a 6 in the bottom, it's a 30-degree reference angle. And so so you always start with your theta, and you ask yourself, okay, where am I at? Okay, I'm going to be on this line, right? And how far out? 2. So we pull it out 2. So that is point A. Okay? And I think that you can easily plot point D as well. So do D next. Ask yourself where 4 negative pi over 3 would be. So pi over 3 is how many degrees, reference angle? 60. And so we wanted that, instead of the counterclockwise movement, we went in the clockwise. So when we go pi over 3 down, we'll be on this line. And we wanted to go 4 out. So 1, 2, 3, 4. Everybody have this for their point D? Okay, so now here's where it gets a little bit tricky. Okay, is when r is negative. Because we're saying that it's a directed distance, or directed length, right? So when I ask you to find negative 5 pi over 3, where's 5 pi over 3 going to be? It's a, what reference angle? 60. So it's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, right? We would be on the same line that D is on, right? But we can't come out in this direction because it's negative. So when it's negative 3, instead of pulling out in the way that you normally would, you have to go backwards, like sucking it in. So instead of being 1, 2, 3 out right here, it's going to be on the same line, 180 degrees removed, 1, 2, 3. So this is your point B. That was B that we were plotting. Directed distance and the directed angle. So we want the angle, but then when we had, blow your mind, right? We wanted to be here. If it had been a positive 3, 5 pi over 3, it would be here, right? But a negative 3 means I don't get to be here. I have to go in the opposite direction, 180 degrees removed. Okay? So now let's look at letter C, point C. Negative 5, negative 3 pi over 4. So always start with your theta. Where's negative 3 pi over 4 going to go? Here, right? Okay, so we know we want to be along this line, but now it is a negative 5, so we don't get to pull it out 5, we have to push it back 5. So 1, 2, 3, 4, 5. And that is our point C. Yes, sir. Nope, you can make it as big as you need to. I had to create these things because I couldn't find good coordinate systems that weren't scanned images from books that were scanned and scanned, and copied and so forth. So when I drew this, I made it 6 out. It could go on for infinity. And again, I was kind enough to give you the ones that we know, the 30s, the 45s, and the 60s, and not put all every well, the 12ths on there. So we're going to work a lot with the ones that we should have memorized, our special items. All right, good questions. Anything else that you have questions about so far? All right, here comes the next one. So now, I want you to plot negative 3 pi over 4. Should be pretty good at this by now, or at least have an idea of how it works. And then we're going to find 3 other coordinates that have that same point, but they without talking about revolutions, between 0 and 2 pi. Okay? Or between negative 2 pi and 2 pi. So we are at 3 and negative 3 pi over 4. So we want to go to negative 3 pi over 4, 1, 2, 3 pi over 4, and we get to go 3 in that direction. So here's our point. Okay. It was a positive 3, so we didn't have to suck it back in. Okay. Now we want to find 3 other things that are the same. So if this is a positive and negative, there will be one that's positive, positive. There will be one that is negative, positive. There will be one that is negative, negative. So you get all 4 possibilities. Yes, sir. So good? Okay. So, any idea what the positive is going to be? Okay. We think it is 3, and then maybe 3 pi over 4. So we get to the same place. Okay. So if we go 1 pi over 4, 2 pi over 4, 3 pi over 4, 5 pi over 4. So 5 pi over 4 with a positive 3 will get us to the same location, at that same point. Okay? So what if we wanted to go somewhere and then suck it back in, right? So we want to have a negative 3 with some angle measured. Okay? So what would that other measure be? Pi over 4. So we go pi over 4 out, and then we had to suck it back in to go negative 3. Okay? That's 2 of them. And now we want to go in the opposite direction and suck it back in. Okay? So if we went in the opposite direction, we can't stop here, right? We have to go all the way around to here, right? And then suck it in. So how far is this? Negative 7 pi over 4, and then pull it back. So negative 3, negative 7 pi over 4. 4 ways to represent the same point. Good question. Fair question. What are we going to use? What would you use this for? And I can't, off the top of my head, I'll have to do some research. I'm sure if I Googled it, they'll tell me all kinds of things that we use it for. We're going to learn how to graph things like r times the cosine of theta and r times the sine of theta using this representation. And so we'll see some things called circles and some things called cardioids and limacons and so forth, right? Some new, which is coming up next week. But to be honest, I don't remember encountering this in my college math, anything I did in college. So I'm sure there are applications, I just don't know what they are. That would make sense. Wave vibrations would be, and frequencies potentially, yes. So, absolutely. So, but like I said, I have not done the research I should have ahead of time, just to say, hey, when do you use this? Why do we need this coordinate plane? Or this polar plane? Coordinate system. All right, so far so good? Other questions? Okay, so here comes the next. So now we have to be able to convert back and forth. So when we have in our rectangular system an x and a y, right, then that forces us or causes us to have an angle theta and an r. So guess what? How do you think we're going to figure out what x is? Well, x is adjacent, right? And r is our hypotenuse. So we're going to use the cosine of theta is equal to the adjacent over the hypotenuse. And we're trying to solve for x, so r times the cosine of theta is our x. And because y is the opposite, we would use the sine. The sine of theta is the y over r, opposite over hypotenuse. And we're trying to get the y by itself, so we would take r times the sine of theta to get our y back. Okay? The other way says, hey, if you have theta and you're trying to find x and y when you know r, right? We would say, okay, since the tangent of theta is equal to y over x, if you want theta back, take the inverse tangent of that y over x. Ask yourself what angle has this for its ratio, or use your inverse tangent button. Okay? If you need to find r, good old Pythagorean theorem helps us with that because we have two legs of a right triangle and a hypotenuse. So x squared plus y squared is r squared, or r is equal to the square root of x squared plus y squared. So we've used this in so many sections when we were talking about r cosine theta, r sine theta, and r equals the square root of x squared plus y squared. All back to our unit circle, which is kind of good because we're going to go back to reviewing for a final here before too long. Okay? So here we go. I want you to convert -3 pi over 2 to rectangular. You could graph it if you wanted to. Not a bad idea. Okay? So if we sketch this real quick, we're going to go 3 pi over 2. So 1 pi over 2, 2 pi over 2, 3 pi over 2. But then we have to suck it back, don't we? Because it's a -3. So when we suck it back 3, we're going to be about right here. Okay, so that's a visual representation. And so that can actually give us the answer as well. But let's verify. So if we're taking r times the cosine of theta, remember here's your r and here's your theta. So our r is -3 times the cosine of 3 pi over 2. So we have to remember, what was the cosine of 3 pi over 2? Cosine started high, ended high, and was low in the middle, right? And so we went down and then up. This was pi and 2 pi. So what is the cosine of 3 pi over 2? 0, isn't it? So we're taking -3 times 0 and getting 0. Okay? Now let's do our sine theta. -3 times the sine of 3 pi over 2 is going to be, well, sine started in the middle, ended in the middle, and was in the middle. So it went high, low, and back to the middle again. So what is the sine of 3 pi over 2? -1. So when we take a -3 times a -1, we get 3. So our rectangular version of this point, rectangular coordinates are 0, 3. So does that match where we think it should be? 0 over 3 up. Make sense? Questions on this one? All right, so you've got 2 more examples to do. One of them is converting 2 pi to rectangular coordinates, and then -3 pi over 4 to rectangular coordinates. So 2 cosine of pi is going to be 2 times -1, right? And we'll get a -2. 2 times the sine of pi will be 2 times 0, and we'll get 0. So we're going to have a -2, 0. Now let's do a quick sketch to verify that that works. Okay? If we're 2 and pi, that means that we're going a directed angle to pi, and then we're going 2 out. Is that the point -2, 0? Absolutely. So they should land in the same spot. Okay? Not necessarily. Yeah, but there will be some that you won't be able to sketch when we get to it. Yeah, obviously the quadrantal angles are going to be very easy. Yep. Make sense? Show your work by sketching. Okay? All right, convert -3 pi over 4 to rectangular. Okay? If you remember your unit circle, we should get -3 square root of 2 over 2, -3 square root of 2 over 2. Now, let's verify that that looks right. Okay? If we go to pi over 4, coming out this way, but then we had to suck it back in, right? Go the opposite. So if we go the opposite, 1, 2, 3, is that going to be the point -3 square root of 2 over 2, -3 square root of 2 over 2? Yes. Okay? Make sense? All right. So converting from polar to rectangular, no big deal. R cosine theta, R sine theta. Converting back is not a big deal either. Okay, now we want to convert from -6, 8 as an ordered pair to R theta. So when we think about this, we're 6 back, 8 up. So we have to figure out what our theta is and what our R is. So we're going to use the tangent of theta equals y over x, right? So we'll end up taking the inverse tangent of the y is the 8, the x is the -6. Now, do we recognize 8 over -6 or 4 over 3 as something that we're supposed to know from our unit circle? Not a special angle, is it? So we'll break out the calculator. And what's the inverse tangent of -8 over -6? What'd you get? So 53.1? Okay, so 53.1 degrees. And the problem is that we're not really, how do we do a -53.1 degrees? Because in order for it to be a function, we've defined tangent to be in the first or the fourth quadrant, positive up here and negative down here, along with our sine. And the cosine is in the first or the second quadrant, positive here, negative here. So this is where we have to kind of muddle through it and sketch it out and see where we're supposed to be. So if it's a 53.1 degree angle, or a -53.1 degree angle, we want to find out what this angle is here. So if this is 53.1, what are we going to do to find If our reference angle is 53.1, what are we going to do to find this other angle? Yes, so 180 minus 53.1 is 126.9. Okay, so we have a 126.9 degree angle. Anybody find it in radians? Calculator was in degree mode. In radians, it would be 0.93. Okay, so if you have that or 0.93 radians, we're halfway there. But the 0.93 radians also has to be converted. So we would take 3.14 radians minus 0.93. And we get 2.21. Okay. So next, we're going to ask you for r. So how are we going to find r if x is negative 6 and y is 8? Negative 6 squared is, and 8 squared is, so we get, should know that one by now, right? We've done them so many times. So r is 10. So now to write this as polar coordinates, we write our r first, and then we write our degrees or radians depending on which one you're using. So you could either have 126.9 degrees, or you could have 2.21 radians. Your book is not going to say radians at the end, but they'll have them in a block of problems that's only dealing with radians or with polar coordinates. Does that make sense? So it'll look like this, and it'll be hard to distinguish from an ordered pair in a rectangular coordinate system. Make sense? So I'd like to put a little RAD behind it, but probably not mathematically legal or whatever, or required. Okay? Not kosher, maybe. Questions on this one? Oh, I have to switch it. We needed to convert this to polar. Yep. So we went from rectangular. This was in our rectangular portion, right? And we're finding a polar coordinate. All right, so now we're down to the very bottom of your bottom box of your notes, and it's asking you to convert to polar coordinates. So we have ordered pairs in rectangular. So do you want to find r first or theta first? Theta. So theta will be the inverse tangent of y over r, y over x. And we ask ourselves, where's the tangent 1? It's 45 degrees, right? I need pi over 4s, okay? So the tangent's 1 and a pi over 4, but we have to ask ourselves, if we're at negative 1, 1, which pi over 4 will that be? 3 pi over 4. So you'll have to kind of sketch this to make sure you get in the right quadrant with this way, or this method. So 1 pi over 4, 2 pi over 4, 3 pi over 4. So theta is 3 pi over 4. And now we need to go and find r. So r is nothing more than the square root of x squared plus y squared, right? Last time we did it was a squared plus b squared. And so 1 plus 1 is, so r is the square root of 2. So as a polar coordinate, we have square root of 2, 3 pi over 4. Make sense? All right, last one, convert to polar. So what angle has a tangent that's a square root of 3? Because square root of 3 over square root or over 3 is all those 3's is a 30, right? There's a 60-degree angle. 60-degree angle in radians is pi over 60 is pi over 3, yep, and 30 is pi over 6. So this is a pi over 3 angle. And we're in the first quadrant, so we don't have to worry about moving anything. And then what will our R be? Good, because we get a 4, and the square root of 4 is 2. So we get 2 pi over 3. Make sense? All right, questions over this? All right. Usually easier to do these in radians. If you give them to me in degrees for whatever reason, I would understand, especially if you're doing the inverse tangent of something that we don't know, one of our non-unit circle angles. But usually we like to have them in radians, just easier to work with. But I won't count it wrong if you give me the right answer in degrees. Okay? If it's in degrees on your assignment, try to leave it in degrees. If it's in radians, try to leave it in radians. That way you work in both types. Okay, assignment. Stop the recording real quick.